Okay, let's unpack this. Imagine taking something as low-level and performance-critical as assembly code, that raw foundational language the computer truly speaks, and making it run faster. Faster than even the most meticulously engineered, decades-old compilers can achieve. That's the audacious, almost fantastical mission of the deep dive we're embarking on today. It's about unlocking hidden performance that, well, we previously thought was already maximized, pushing past what we believed was the absolute ceiling.
Yeah, and what's truly fascinating here, I think, is how this groundbreaking research bridges two seemingly disparate worlds. You've got the abstract generative power of large language models, these incredible text generators we all know about now, and then you have the concrete byte-level optimizations required for peak hardware performance.
Right, two totally different ends of the spectrum.
Exactly. And we're talking about LLMs being fine-tuned with sophisticated reinforcement learning techniques like Proximal Policy Optimization, or PPO, fine-tuned to genuinely push the boundaries of assembly code optimization, really into territory that was once thought impossible for AI.
Okay, so our mission in this deep dive is to crack open a truly groundbreaking new paper. It's titled Improving Assembly Code Performance with Large Language Models via Reinforcement Learning. We'll be zeroing in on the intricate technical details about how and what of this cutting-edge technology. We want to give you a crystal clear understanding of its profound implications without getting bogged down in, anything else. We're focused purely on the ingenious engineering behind this breakthrough and what it means for the future of software. Now, you might be sitting there thinking, wait a minute, don't compilers already do this? No, don't they take my elegant high-level C code and magically transform it into super fast machine instructions? And yes, you're absolutely right. Compilers like GCC-Do3 are the undisputed titans of traditional code optimization. There's a result of decades of brilliant human engineering. But here's where it gets really interesting. Despite all that sophistication, these traditional tools have inherent limitations.
Indeed. They do. While compilers are marvels of engineering, absolutely, they operate under certain structural and computational constraints. And, ironically, these constraints create a significant opportunity for entirely new approaches, particularly with large language models. The domain of fine-tuning low-level code for peak performance is notoriously complex. It's a true frontier in computer science.
So let's break this down a bit. Why exactly is optimizing assembly code such a monumental task? And why isn't existing compiler technology already the perfect final word on it? What's the inherent challenge that leaves room for AI to step in?
Well, assembly code sits right at the bottom of the software stack. It's just one step removed from the raw binary instructions that your computer's processor executes directly. It's the closest you can get to the hardware without actually, designing a new silicon chip.
Wow, okay, so
Yeah,
really close to the metal.
exactly. And this extreme proximity offers a truly fine-grained, granular level of control over execution. It allows for performance improvements that are incredibly difficult, if not outright impossible, to express or realize in higher-level languages like C++ or Python. Think of it like this. In C, you might tell a function to multiply two numbers. Simple enough. But in assembly, you're literally telling the processor to load this number into that specific register, then execute this specific multiplication instruction, then store the result right there.
That level of direct instruction, yeah, I can see how that makes assembly code crucial in performance-sensitive domains.
Yeah.
Places where every single clock cycle counts. Areas like operating systems, maybe high-frequency trading platforms, or core rendering engines of modern video games, where even a tiny fraction of a second makes a huge difference.
Precisely. That ultimate level of control is the key for performance.
I can absolutely see how that control is appealing. It's like being able to precisely control every individual cog and lever in a machine rather than just hitting a general go faster button. But that precision, that low-level nature, wouldn't that also be a disadvantage for an LLM? I mean, assembly code isn't exactly common, flowing human text or widely available source code, right? It's highly specialized stuff.
You've hit on a critical point there.
Yes.
This low-level, specialized nature poses a significant challenge for LLMs. Assembly code is relatively rare compared to, say, Python or JavaScript code floating around online, and consequently, it may be heavily underrepresented in the colossal pre-training corpora that LLMs learn from, the massive data sets they're trained on.
Right, they're trained on the vastness of the internet, and assembly code snippets are just a tiny fraction of that.
Exactly. So this scarcity means it can be much harder for these models to effectively reason about assembly's intricate behavior, its complex instruction sets, and its optimal transformations, especially without specific targeted training. They kind of lack the intuitive understanding of assembly's grammar and idioms that they might have for natural language or higher-level programming languages.
Right. Okay. So even if assembly offers this incredible fine-grained control and performance potential, we've relied on compilers for decades to handle this complexity for us. How do modern compilers, like our workhorse GCC Daijo 3, actually approach this optimization? And despite all that brilliant engineering, where do they still fall short? Where's the opening for LLMs?
Okay, so modern compilers like the GCC suite, especially at that aggressive Nacho 3 optimization level, employ a vast arsenal of rule-based transformations. They meticulously analyze your high-level source code and apply a predefined series of optimization passes.
Right.
Each pass is a distinct algorithm designed to improve specific aspects of the code. You have things like dead code elimination.
Right, getting rid of useless instruction.
Exactly. Or loop unrolling, which duplicates loop bodies to reduce overhead, or common sub-expression elimination, which avoids recalculating values that have already been computed. Each of these passes aims to squeeze out just a little bit more performance.
It sounds like a highly sophisticated assembly line almost, where each station has a specific recipe or set of instructions designed to make a particular part of the program more efficient.
That's a great way to put it. However, this sequential, rule-based design introduces a fundamental hurdle. It's known as the classic phase ordering problem. The sequence, the order in which these various optimization passes are applied, can drastically and sometimes counterintuitively affect the final performance of the generated code.
Ah, okay, so it's not just what optimizations you do, but when you do them relative to each other.
Precisely. Imagine you have a set of specialized tools, say a wrench, a screwdriver, and a hammer, and you're trying to fix something complex. The order you use them in, and even whether you use one tool before or after another, fundamentally changes the outcome. Applying one optimization might enable another one down the line, or it might accidentally undo the benefits of a previous one. It gets complicated fast.
I see. And because the number of possible sequences is huge.
Astronomically vast. And the interactions between passes are so complex, traditional compilers face inherent limitations in consistently finding the truly optimal code. So despite decades of meticulous tuning and brilliant work by performance engineers, they often leave significant performance on the table. It's just unavoidable with that structure. This systemic limitation is precisely where the opportunity for LLMs emerges, because they aren't bound by those rigid, predefined compiler rules. It's a fundamental crack in the wall of traditional optimization that LLMs can potentially exploit.
So even with all that human ingenuity poured into compilers, they still hit a wall because of this phase ordering problem. It's like trying to navigate an incredibly complex maze where every turn you take influences all future turns in unpredictable ways, and you can't easily backtrack or see the whole picture. That makes perfect sense for why there's still room for improvement. But what about super optimization? That sounds like it's explicitly designed to find the most optimal code possible. Doesn't that solve it?
Super optimization is indeed a fascinating and theoretically powerful alternative. Its core goal is to search for the most performant variant among all programs that are functionally equivalent to a given piece of code. Usually they start with the compiler's output. In principle, this exhaustive search strategy could yield truly optimal code for a given task. Sounds like the holy grail of code optimization, right?
It really does, like the ultimate answer. If it can yield optimal code, why isn't it the standard everywhere? Why isn't every compiler using this approach?
Well, its theoretical appeal, unfortunately, clashes head-on with some significant practical limitations. The computational challenge is immense. The search space for functionally equivalent programs just grows exponentially with the size of the program. This makes exhaustive exploration computationally infeasible for anything but the smallest, most trivial snippets of code.
Ah, the combinatorial explosion problem.
Exactly. Imagine trying to find the single best path through a labyrinth with a quadrillion possible routes. Even for just a short stretch of code, it's just not practical. Furthermore, prior foundational work on super optimization has primarily targeted very specific, simplified cases, like loop-free, straight-line code, little chunks without complex logic. For these cases, it's more tractable to formally verify that the optimized code is truly semantically equivalent to the original, mathematically proving they do the exact same thing. But as a result, these traditional super optimization approaches are just not directly applicable to most real-world programs. Real programs commonly include complex loops, intricate control flow, external dependencies, all things that explode the search space and make verification incredibly hard.
Okay, so if traditional compilers hit a wall with the phase ordering maze and super optimization is brilliant but simply too computationally demanding for real-world programs,
Mhm.
what's a genuinely new path forward? This is where the LLMs step in, right? It
Mm.
seems like this paper is really trying to bridge that gap with a fundamentally different approach.
Precisely. If we connect this to the bigger picture, this work presents a compelling and, I think, novel framework, using the adaptive learning capabilities of reinforcement learning to overcome the inherent rigid limitations of traditional rule-based compilation. The ability of LLMs to generate novel, sometimes unexpected code sequences combined with a precise feedback loop allows them to explore optimization strategies that compilers, constrained by their predetermined rule sets and phase orders, simply can't discover on their own.
That's the core innovation then, leveraging LLMs to act as sophisticated optimizers for low-level code. But how does that actually work in practice? What's the fundamental idea, the core engine behind this?
Okay, the core idea, and you can see this conceptually in Figure 1 of the paper, is that an LLM generates optimized assembly code. It's a generative process. The process begins by providing the LLM with an input. This input contains two key pieces, the original C program and its corresponding baseline by 8664 assembly output generated by GCC03.
The standard compiler output.
Right, the industry standard baseline. The LLM then takes these as context and generates its own candidate for an improved assembly program. But this isn't just a blind guess. It's part of a sophisticated iterative feedback mechanism driven by reinforcement learning.
And what does that feedback mechanism look like? How does the LLM know if its freshly generated assembly is actually improved and not just, broken or slower?
That's where the reinforcement learning really shines. The LLM receives crucial feedback through a carefully designed reward function. This function meticulously evaluates two critical aspects of the generated assembly. First, its functional correctness. Does it produce the exact same output as the original C program for a given set of test cases? That's paramount. And second, its execution performance, measured precisely against that GCC03 baseline. The ultimate aim here is to discover and achieve fine-grained performance improvements that push beyond what traditional compiler optimizations can deliver, sometimes finding completely novel ways to run faster.
So it's a bit like a trial and error process, but with a very smart, automated way to evaluate what error and success truly mean in terms of correct and faster code. And the paper specifically mentions Proximal Policy Optimization, PPO, as the reinforcement learning algorithm they used. For those of us less immersed in the deep learning trenches, can you tell us more about PPO? Why is it a particularly good fit for this kind of complex, iterative optimization task?
Sure. PPO, or Proximal Policy Optimization, is a robust and pretty widely adopted reinforcement learning algorithm. It's popular for good reason. It's particularly effective because it brings stability to the training process. It does this by ensuring that each policy update, basically each time the LM adjusts its strategy for generating code, remains relatively close to its previous strategy.
Okay, so it prevents wild swings in strategy.
Exactly. Think of it like teaching a child to ride a bike. You don't want them making huge, erratic turns that send them crashing immediately. PPO ensures their steering adjustments are small, stable, and incremental. It prevents large, potentially counterproductive changes that could destabilize the entire learning process. This allows for more efficient and reliable convergence to better solutions.
That's a great analogy. It sounds like it keeps the learning on a more steady, controlled path, preventing the model from making drastic, potentially harmful changes based on just single feedback instances.
Precisely. And the researchers cleverly framed this intricate task using an analogy from game theory, something called a contextual multi-armed bandit problem.
Okay, multi-armed bandit. Sounds interesting. How does that apply here?
Right, let's demystify that. Imagine you're at a casino with a wall of different slot machines, the bandits. Each one has a hidden, unknown payout rate. Your goal is to figure out which machine gives you the best return by pulling its arm, right? You want to maximize your winnings. In this specific code optimization scenario, the context is the problem itself. The unique C program, its GCC-03 assembly baseline, and all the test cases. This is the information you have before you act. The action is the LLM generating a brand new candidate assembly program. That's like pulling the arm of one of the bandits.
Yeah.
And the reward function is how the quality of that generated program is immediately evaluated, whether it's correct and how fast it runs. That's your payout from the machine.
Ah, I get it. Context, action, reward. Simple but powerful framing.
Yeah. And they use a critic model within the PPO framework to estimate the advantage of taking a particular action in a given context. This helps guide the LLM towards better actions over time. Crucially, the rewards computed directly from the correctness and execution time of the generated program. They avoid the need for a separate, potentially complex, and error-prone reward model. This direct feedback loop simplifies the process and makes it highly effective for this specific task.
That's quite an elegant solution for the feedback loop. It streamlines the whole process of knowing if the LLM's guess was actually a good one. Speaking of rewards, the paper discusses two fascinating variants of their reward function: correctness-guided speedup, or CGS, and speedup only, SO. Can you walk us through those and highlight how they differ in guiding the LLM's learning?
Absolutely. The design of the reward function is paramount in reinforcement learning. It's literally the signal that tells the LLM what behavior to optimize for. It shapes everything. They started by defining two auxiliary metrics to build these reward functions. First, pass, A. This is simply the fraction of test cases passed. It directly indicates the functional correctness of the generated assembly. If it passes all tests, passes 1.0, if half, 0.5, and so on. Pretty straightforward. Second, speedup, pass A. This is calculated as the execution time of the baseline GCC03 program divided by the execution time of the LLM-generated program. A value greater than 1.0 means the LLM's code is faster, and the higher the number, the better the performance relative to GCC03.
So pass is about accuracy, getting it right, and speedup is about raw performance, doing it fast.
Got it.
Now, how do these two metrics combine into the CGS and SO reward functions?
Right. Let's look at the two reward function variants they explored. Number one, correctness-guided speedup, CGS. This variant provides what they call a dense training signal. That means it gives continuous feedback even if the model hasn't achieved perfection yet. So if the generated assembly fails to compile at all, the LLM gets a harsh reward of -1. That's a strong penalty for a fundamental failure. Tells the model, don't do that again.
A clear negative signal.
Yes. Then, if it compiles successfully but some tests fail, the reward is simply pass. This is clever because it provides partial credit. If the code passes, say, 70% of tests, it gets a 0.7 reward. This is an intermediate signal that it's on the right track towards correctness, even if not fully there yet. It encourages fixing correctness issues incrementally.
Okay, so it nudges it towards correctness.
Exactly. But crucially, if all tests pass, meaning pass 1.0, the reward shifts. It becomes 1 plus us in speedup. Here, alpha is a carefully chosen constant that controls the relative importance of speedup once full correctness is achieved. This encourages both functional correctness as a prerequisite and then aggressively drives for performance gains.
Makes sense. Correctness first, then speed. What about the other one, SO?
Number two, speedup only, SO. This is described as a more direct and sparse objective. It's much less forgiving. If the generated assembly fails to compile, or if any single test case fails, the reward is a flat 0. No points. There's no partial credit for correctness here at all. The model gets nothing for being almost correct.
Wow, okay. All or nothing on correctness.
Pretty much. Only if all tests pass and the generated program is demonstrably faster than the baseline GCC-03 code does it receive a non-zero reward. And that reward is simply speedup, as LO. This variant strictly rewards only the terminal goal, achieving both perfect correctness and a measurable speedup. If it's correct but slower, it also gets a 0.
So CGS gives you encouragement and intermediate scores along the way, trying to gently guide the model towards correctness first, then speed. While SO is much more of a pass-fail than measure speed kind of approach. That makes a lot of sense for a highly technical field where code either works perfectly and fast, or it's effectively useless, right? So with the what and how of the RL framework laid out, let's talk about the real battlefield where these LLMs were put to the test: the dataset and the experimental setup. Any groundbreaking claim needs solid, undeniable evidence, and that absolutely comes from a meticulously designed experiment. This paper constructed a truly fascinating dataset, it seems.
Indeed. The quality, relevance, and representativeness of the dataset are absolutely crucial for evaluating the effectiveness of any machine learning approach, especially in a specialized and performance-critical domain like assembly code optimization. A poorly chosen dataset would, frankly, render any results questionable.
Totally. So where did they source the programs for this challenging benchmark? And what exactly did each piece of data look like for the LLM?
The C programs for their dataset were drawn from CodeNet. CodeNet is a massive, publicly available corpus of competitive programming submissions. Think of it as a huge collection of solutions to coding challenges from online contests like Top Coder or Codeforces.
Ah, okay. So lots of small algorithmic problems.
Exactly. And each instance they used in their dataset was carefully structured as a tuple, CPT. Here, C is the original C source code provided by a competitive programmer. P is the corresponding by 8664 assembly code generated by compiling that C program with GCC at its Nactio 3 optimization level. This serves as the high-quality, industry-standard baseline the LLM is trying to beat. And T is the test set, composed of specific input-output pairs designed to verify the program's correctness.
That makes perfect sense for the inputs, but how did they generate those test outputs? The competitive programming sites often have their own reference outputs, don't they? Why not just use those?
That's a great question. And they took a very crucial and insightful step here that really speaks to the rigor of their methodology. While they adopted the test input SLE from prior work that utilized CodeNet problems, they deliberately discarded the pre-existing CodeNet output labels. Instead, they meticulously regenerated each expected output, P, by actually executing the original C submission on the given input elite.
Oh, interesting. Why go to that extra trouble?
Well, the reason for this, as the paper explicitly notes, is that many CodeNet programs are not accepted solutions, and even accepted ones do not reliably pass all test cases for all possible inputs. Competitive programming code can be quirky, By executing the specific C code provided for each instance, they ensured that their test cases accurately and reliably reflected the precise behavior of that particular C program, even if it had slight bugs or edge cases. This guaranteed the integrity of their correctness checks.
That's a very thorough and thoughtful approach, definitely guaranteeing the integrity of their correctness checks. Smart.
And with CodeNet containing millions of submissions, how did they select the specific programs for their study? Was it just a random sample, or was there a deliberate strategy involved?
Oh, it was far from random. Given the immense scale of CodeNet, they employed a very specific sampling strategy. They wanted to focus on programs that represented a challenging performance-critical subset. Specifically, they sampled programs that exhibited the highest relative speedup when compiled with GCC03 compared to GCC0. A 0 basically means no optimization.
Okay, that's a very deliberate and interesting sampling strategy, selecting programs where the compiler already makes a big difference. What was the dual purpose behind selecting programs that already showed a substantial improvement from basic to aggressive compiler optimization? It seems like they were trying to make it harder for the LLM from the start. You've precisely identified the brilliance of this strategy. It served two critical purposes. First, it inherently favored programs with complex logic. Programs that would otherwise perform poorly under GCC0 but could be significantly optimized by the RESO3 compiler. This meant they were selecting programs where compiler optimization truly made a meaningful difference, focusing their efforts where performance gains were actually possible and significant.
Okay, focus is the effort. What's the second purpose?
Second, and perhaps even more crucially, it created a more challenging setting by starting from code that has already benefited from aggressive compiler optimizations.
Yeah.
By selecting problems where the traditional compiler had already done its expert best, they were setting an extremely high bar for the LLM. The goal wasn't just to optimize any code, but to beat the compiler's expert solution. If an LLM could generate code that further improved upon GCC03 on these already optimized problems, it would be a powerful indicator that the model could truly outperform the traditional compiler in demanding scenarios.
That's a brilliant way to truly test the limits of these LLMs. It's like asking them to beat the reigning world champion, not just some random amateur. Very clever. So what did the final data set look like in terms of size and typical program complexity for both training and evaluation?
The final dataset was quite substantial. It consisted of 7,872 distinct programs for training the models, and then a separate held-out set of 200 evaluation programs to ensure unbiased assessment. As summarized in Table 1 of their paper, the average C program in the dataset was relatively compact, typically around 22 lines of code. This translated to an average of about 130 lines of assembly code after GCC-03 compilation. On average, each problem also came with about 8 or 9 test cases to check correctness. So these are compact, but often algorithmically complex, functions typical of competitive programming challenges. They're perfect for testing optimization in a controlled, yet realistic environment.
Now that we know about that meticulously crafted data, let's move to the operational side, the prompt structure. How is the input actually fed to these LLMs, and what exactly were the models instructed to generate?
Right, the prompt. For each problem instance, the LLM received a specific prompt that included 2 primary components. First, the original C source program. Second, the GUI 8664 assembly code generated by GCC-03 for that C program. This GCC03 assembly was a crucial reference point, as we discussed. Critically, all test cases were explicitly withheld from the model during the generation phase. The model didn't get to peek at the answers.
Okay, no cheating.
Exactly. And the LLM was given a clear instruction: generate only optimized by 8664 assembly code. No additional descriptive text, no comments, no extraneous output, just the raw assembly. This focused the model solely and exclusively on the task of producing the raw, optimized assembly instructions.
Got it. Pure assembly output. And once the LLM generated its assembly, how was its performance then evaluated? What were the key metrics they used to judge success, both in terms of correctness and speed?
They employed a comprehensive set of metrics to ensure a holistic evaluation. It wasn't just about speed. For correctness, they measured two distinct but related aspects. First, compile pass. This was simply the percentage of problems where the LLM-generated assembly code successfully compiled into an executable binary without errors. If it didn't compile, well, it couldn't be run. Basic sanity check. Second, test pass. This was the more stringent metric. It measured the percentage of problems where the compiled LLM-generated code passed all test cases correctly. If even a single test case failed, it counted as a total failure for this metric.
Okay, so one strike and you're out on the test pass metric. That reflects a crucial real-world requirement, right? In performance-critical systems, partial correctness often means total failure.
Precisely. And for performance, they measured the relative speedup over the GCC03 baseline. This is where the practical utility really shows. Now, an absolute vital detail in their evaluation methodology was how they assigned a 1x speedup. Any candidate program that failed to compile, failed any test case, or was actually slower than the baseline GCC03 output, all of those were assigned a default speedup of 1x.
Okay, so 1x means no improvement or worse.
Exactly. This is extremely important because it represents the practical reality. If the LLM's output isn't perfect, if it's incorrect or slower, you would simply fall back to the reliable GCC03 output, meaning you gain nothing. So 1x is the effective floor. They also reported speedup not just as an average, but crucially in percentiles the 25th, 50th, which is the median, and 75th percentiles. This gives a much clearer, more nuanced picture of the distributional behavior of the performance gains. It shows if improvements were consistent across problems or only happened for a few outliers.
That's a very robust and pragmatic set of metrics, clearly designed to capture the real-world utility of the generated code, not just some theoretical peak performance. And who are the contenders in this fierce code optimization battle? Which LLMs did they put to the test against each other and eventually against their PPO-trained model?
They fielded a truly broad spectrum of 21 LLMs. It was quite a lineup, spanning various architectures and development philosophies. This allowed for a thorough comparative analysis. These included cutting-edge, frontier proprietary models from the big tech companies. Think GPT-4o, GPT-4 Mini, Gemini 1.5 Flash 001, and Claude 3.5 Sonnet, the latest and greatest general-purpose models. Then there were various prominent open-source families, including different sizes and instruction-tuned versions of models like Llama, DeepSeek, and Quinn, also some models specifically distilled from DeepSeek R1, and notably, specialized compiler foundation models. These are models explicitly pre-trained on assembly code and designed for compiler-related tasks, like a DILM Compiler 7b and DILM Compiler 13b.
Oh, interesting. So they included models specifically built for compiler-like tasks.
Yes, and it was particularly interesting to see how their specialized training would stack up against the more general-purpose models, especially when confronted with an optimization task that might be slightly different from what they were originally designed for.
That's an incredibly comprehensive lineup. 21 models is a lot to test. How did they ensure that the performance measurements were accurate and fair, given, the notorious variability of real-world execution times on physical hardware? It's a tricky business getting consistent benchmarks.
You're absolutely right. Benchmarking low-level code on real hardware is notoriously difficult due to microarchitectural noise, system variability, all sorts of things. To mitigate this and ensure accurate, reproducible performance evaluation, they used Hyperfine. It's a robust and widely respected command-line benchmarking tool specifically designed for this kind of thing. For each program's execution, they followed a strict protocol. First, they performed several warm-up runs. This helps prime the processor's caches and instruction pipelines, getting the system into a stable state. Then they discarded the initial 3-timed executions just to further stabilize the system and throw out any initial jitters. Finally, they averaged the next 10-timed runs. This rigorous process helps us significantly reduce the impact of environmental factors, transient background processes, and hardware fluctuations that can otherwise introduce substantial variability into performance measurements.
That's a smart and necessary detail, really accounting for the realities of benchmarking on physical hardware. Good methodology. And for the actual reinforcement learning training, the PPO part, Which specific LLM did they select as the base for fine-tuning, and why that one? What was the hardware setup for that intensive training?
Okay, for the core reinforcement learning fine-tuning, they selected Qwen 2.5 Coder 7B Instruct as their base model. Their rationale was strategic. Among the models they initially evaluated before fine-tuning, Qwen 2.5 Coder 7B Instruct showed the strongest correctness results and substantial room for performance improvement. This meant it was already pretty good at generating functionally correct code, which gave the RL process a solid foundation to build performance on top of. It wasn't starting from complete scratch on correctness.
Okay, so it had a good starting point. Did they consider using those compiler-specific models?
They specifically mentioned that they intentionally avoided using the compiler-specific foundation models for the PPO training. They wanted to preserve the generality of their approach. This demonstrates that a powerful, general-purpose LLM can be adapted to this highly specialized optimization task, rather than requiring a model that was already pre-specialized for compilers, which is quite an interesting finding in itself. The training itself was performed on a single powerful node equipped with 4 NVIDIA A100 GPUs. They used the VRL framework for the PPO fine-tuning. This framework provides a task-specific environment for handling the compilation, test execution, and runtime measurement, delivering that direct scalar feedback, the reward to the model for continuous learning.
Got it. A powerful setup for a demanding task. So with all these models lined up, a challenging dataset prepared, and the sophisticated testing rig ready, let's finally dive into what they actually discovered. The results, frankly, sound like they'd be quite compelling, especially for their PPO-trained model.
Yes, and this truly raises an important question. Can LLMs, despite their general-purpose nature, genuinely surpass decades of dedicated compiler engineering? The empirical data from this study suggests a resounding yes, at least under specific conditions, and it demonstrates a clear, exciting path forward for discovering entirely new, high-impact optimizations.
Okay, so let's first get a sense of the general performance. How did most of the 21 LLMs, the baseline models without the special PPO training, fare on this incredibly challenging assembly optimization task? Were they able to beat GCC03 right out of the box?
Looking at Table 2 in their paper, the picture is quite clear. Most of the general-purpose LLMs struggled, a lot. The vast majority of models yielded only a 1.00x speedup, which, as we discussed, effectively means they either failed to compile, produced incorrect outputs that didn't pass all tests, or were simply slower than the GCO3 baseline. No gain.
So basically no improvement for most of them.
Pretty much. And their compile and test pass rates were also remarkably low, often in the single digits or even 0 for some models. This powerfully underscores the inherent difficulty of the task for general-purpose LLMs without highly specialized, targeted training like the PPO approach. It's just not a task they're naturally good at just by being large language models.
So it's definitely not a case where you can just throw any old LLM at this problem and expect miracles.
Got it. Which of the baseline models, meaning those not fine-tuned with PPO, performed the best? Were there any standout performers among the off-the-shelf models? Among the baseline models, 2 proprietary models, Claude 3.5 Sonnet and DeepSeek V3, were the clear standouts, relatively speaking. Claude 3.5 Sonnet achieved a robust 94.5% compile pass rate, which is pretty good. A solid 58.5% test pass rate, meaning it got more than half right, and an average speedup of 1.22x over GCC03. DeepSeek V3 also shows strong capabilities, with a 94.0% compile pass, 43.0% test pass, and a 1.21x average speedup. So these models, relatively speaking, performed quite well given the challenge, showing some inherent capability. It's also worth noting that some other models, like DeepSeek R1, apparently completely failed to generate any valid assembly whatsoever. 0 success, highlighting the wide spectrum in capabilities across the LM landscape for such a specialized task.
Right, and what about those compiler foundation models we discussed earlier, the ones specifically pre-trained on assembly code? Did their specialized training actually give them an edge in this optimization challenge?
That's a really interesting part of the results. Elm Compiler 13b, the larger of the 2 compiler foundation models, did show strong raw performance in its base form. It achieved a 60.5% compile pass rate, a 59.5% test pass rate, and a respectable 1.34x average speedup. This was, in fact, the highest average speedup among all the models that were not fine-tuned with PPO. So its pre-training did seem to help.
Okay, so the specialized pre-training paid off initially?
It seems so. However, their fine-tuned variants, like Elm Compiler 13b Atid, fine-tuned downstream, performed quite poorly on this specific optimization task. The paper suggests this is likely because these fine-tuned versions were adapted for different, albeit related, compiler tasks,
Things like disassembling by 8664 and ARM assembly into LLVMIR, which is an intermediate representation compilers use internally. That's different from directly optimizing assembly code for execution performance. So while their pre-training was in the right domain, their subsequent fine-tuning wasn't precisely aligned with this specific objective of generating faster executable code.
Ah, okay. Subtle but important difference in the fine-tuning goal. So a decent baseline performance from some top models, and the specialized compiler models were a mixed bag. The raw pre-trained ones showed promise, but the fine-tuned ones struggled. But now let's talk about the true star of the show, the model that was fine-tuned specifically with reinforcement learning using PPO. How did Qwen 2.5 Coder 7b PPO, ours as they label it, perform? Did it live up to the promise?
Oh, it absolutely did. Qwen 2.5 Coder 7 BPPO truly dominated the competition. It showcased the real power of this reinforcement learning approach for this task. It achieved an exceptional 96.0% compile pass rate and an equally impressive 96.0% test pass rate, demonstrating near-perfect correctness on this challenging dataset.
Wow, 96% on both compile and test pass. That's incredibly high.
It really is. And more importantly, it delivered an average speedup of 1.47x over the GCC 03 baseline. Now compare that to the base Qwen 2.5 Coder 7b instructor model's 1.1x speedup before PPO training. That's a huge jump, and it's also significantly higher than the best baseline model, the ILM compiler 13b, which was at 1.34x.
Wait, so a jump from 1.7x average speedup for the base model to 1.47x after PPO training. That's not just an incremental improvement, that's a massive leap, nearly 50% faster on average than the optimized compiler output. How did they achieve that with the general purpose model, and how did it stack up against all the other 20 models across all the metrics?
It's quite remarkable, isn't it? Qwen 2.5 Coder 7b PPO outperformed all 20 other models evaluated across every single metric they considered: compile pass, test pass, average speedup, and importantly, all speedup percentiles, 25th, 50th, 75th. It swept the board. What's particularly significant, and truly speaks to its robust performance, is that Qwen 2.5 Coder 7b PPO was the only model to exhibit meaningful speedup even at the 25th percentile. It achieved 1.21x speedup at the 25th percentile. For all other models, their 25th percentile speedup was just 1.00x.
Meaning that for at least a quarter of the test cases, all the other models offered absolutely no improvement over the baseline GCC03.
Yeah, exactly.
This indicates that Qwen 2.5 Coder 7b PPO isn't just getting lucky with a few outlier examples where it finds a huge optimization. It provides consistent, reliable performance gains across a wide range of programs. That's a true indicator of practical utility.
That consistent gain, even at the lower end of the spectrum of programs, is a huge indicator of its practical utility. It means you can rely on it to deliver improvements more often than not. Fantastic result. Now let's talk about that ablation study on reward function design. Earlier, we discussed CGS, the correctness-guided speedup with those helpful intermediate correctness signals, versus SO, the speedup only, which is a sparse, direct signal-only rewarding speedup after correctness, is perfect. What did the results show about which reward signal was ultimately more effective for guiding the LLM towards maximum performance? Right, the ablation study on reward function design. It's clearly summarized in Table 3 of the paper and provided very insightful results. Both the correctness-guided speedup, CGS, and the speedup-only SO variants, when applied to fine-tune Qwen 2.5 Coder 7b, achieved very high compile and test pass rates. Both got close to that 96% mark, indicating they were both effective at driving correctness. However, when it came to raw performance, the speedup-only SO variant consistently yielded better optimization. It achieved that top average speedup of 1.47x compared to CGS's still respectable 1.38x. That 0.09x difference might sound small, but it's actually quite significant in the context of low-level optimization, where gains are hard-won.
So even though CGS provides what seems like helpful intermediate correctness signals, the SO variant, which is more direct and sparse, basically a win big or get nothing approach on speedup, actually led to better overall optimization results. Why do you think that is? What's the underlying mechanism at play here? It seems a bit counterintuitive.
Well, the analysis by the researchers, and it aligns with a common understanding in reinforcement learning, suggests that removing intermediate shaping appears to help the model focus on terminal objectives. Essentially because the base model, Qwen 2.5 Coder 7b instruct, already started with a relatively strong baseline correctness, remember, around a 61.0% test pass rate. Even before fine-tuning correctness wasn't the primary bottleneck for improvement anymore. It was already decent at producing correct code.
Ah, okay. So correctness wasn't the main hurdle it needed to overcome.
Exactly.
In such a scenario, giving the model a reward that's only tied to actual speedup, and only when correctness is perfect, like the SO function does, provides a stronger, more unambiguous training signal for the reinforcement learning process. The model isn't distracted or satisfied by incremental correctness gains along the way. Instead, it dedicates its entire learning capacity to the ultimate hardline goal, maximizing performance. This demonstrates that for certain tasks, especially when a strong correctness baseline already exists, a direct, hardline reward system can be more effective than a more forgiving, progressively shaped one. It forces the model to be laser-focused on the truly challenging aspect, which in this case was raw speed.
That's a crucial insight for designing these reinforcement learning systems.
Yeah.
The right signal, and perhaps more importantly, the right level of sparsity in that signal, is paramount depending on where the model starts.
Fascinating. Now let's move to another key ablation study, the importance of including that GCC03 baseline assembly in the prompt. This sounds like it could be a really significant factor, almost like giving the LLM a cheat sheet or a starting point.
It certainly is, and the results of this ablation study were incredibly dramatic, perhaps the most dramatic finding. Remember, in their primary evaluation, the LLM always received the GCC03 baseline assembly along with the C source code in the prompt. This baseline provides a high-quality, functionally correct starting point. However, the researchers investigated a more challenging setup. Could the LLMs directly compile C code into highly performant assembly without relying on this compiler-generated baseline? This would test the LLM's raw ability to optimize from scratch.
So a true direct C-to-optimize assembly translation by the LLM without that GCC03 hit. What happened when they removed that baseline assembly from the prompt? Was it able to perform the optimization on its own?
The results, as clearly shown in Table 4, were nothing short of catastrophic. Removing the baseline assembly led to a severe degradation across the board. For their star performer, Qwen 2.5 Coder 7B PPO, its performance plummeted from an outstanding 96.0% correctness and 1.47x speedup, down to a staggering 0.0% correctness and just 1.00x speedup.
0% correctness. It completely failed.
Completely. It failed to generate any correct or faster code when deprived of the GCC03 baseline. And even strong baseline models like Claude 3.5 Sonnet suffered substantial declines. Its compile pass rate dropped from 94.5% down to 53.0%. Its test pass rate cratered from 58.5% to a mere 16.0%. And its average speedup fell from 1.22x to a marginal 1.07x.
Wow, that's a truly massive drop-off across the board. It unequivocally shows that the compiler's output isn't just a helpful suggestion, it's an absolutely critical piece of information, perhaps even acting as a necessary scaffolding for the LLM's optimization process.
Absolutely. The conclusion from this ablation study is crystal clear. Direct compilation from C to optimized assembly remains challenging for current LLMs when starting from scratch. They just can't do it reliably yet. The GCC03 compiler output provides an incredibly reliable, high-quality reference point. It acts as an effective starting point for reinforcement learning. It effectively gives the LLM a highly optimized, functionally correct example of what the code should look like. This allows the LLM to focus its sophisticated reasoning and generation capabilities on finding even better, more subtle optimizations, rather than struggling with the basic and apparently very difficult task of generating functionally correct assembly from raw C code. This is a critical design choice in their framework that highlights the LLM's role here as a refiner and enhancer of existing compiler output, rather than a full replacement for the compiler itself.
That makes perfect sense. It's like giving an artist a beautifully rendered master painting to refine and elevate, rather than asking them to paint a masterpiece from a completely blank canvas with no reference whatsoever. This approach seems to allow the LLM to really shine at what it's truly good at, making subtle yet powerful tweaks and discovering new, unexpected transformations on top of a solid base. Let's look at a concrete example of this genius that the LLM discovered, the Popint case study. This is where it really shows its ability to think different, right?
Yes, this case study, vividly illustrated in Figure 2 of the paper, is perhaps one of the most compelling pieces of empirical evidence for the LLM's advanced capabilities. It shows a representative example where the LLM, particularly GPT-4o and Claude 3.5 Sonnet in their initial tests, even without PPO, discovered an optimization that truly surpassed what a state-of-the-art traditional compiler like GCC03 could achieve.
Okay, lay it out for us. What was the original C code doing, and how does GCC-03, the expert compiler, handle it?
The original C function in question computes the population count. That's simply the number of set bits, with a value of 1 in an unsigned long integer, a common enough task in certain algorithms. The C code implemented this using a straightforward canonical loop. It repeatedly shifts the input number to the right by 1 bit and adds the least significant bit, 0 or 1, to a running result variable. It continues doing this until the input number becomes 0. Pretty standard bit manipulation loop. Now, when GCC03 compiles this C code, its output assembly diligently preserves this exact loop structure. It translates the bitwise operations, like shift right, bitwise and conditional branches directly into corresponding assembly instructions. It stays very close to the original high-level logic of the C loop. This is typical compiler behavior. It optimizes the given structure, maybe unrolls the loop a bit, but rarely fundamentally rewrites the whole approach.
Okay, so the compiler translates the loop faithfully. And in stark contrast, what did the LLM-generated code do instead? How did it achieve such a dramatic improvement?
In stark contrast, the LLM generated a significantly more concise and profoundly more efficient implementation. It completely replaced the entire multi-instruction loop structure with a single, highly specialized popcrant instruction.
Popcrant, just one instruction. What exactly is that instruction, and why is it so much better than an entire loop of operations? It sounds almost too simple to be true.
The popcrant instruction is a powerful, specialized hardware-level instruction supported by modern x86-64 processor architectures. It's literally designed by the chip makers to perform the exact population count computation in one single CPU operation. By intelligently recognizing the high-level semantic intent of the C loop that it was calculating the population count, and then knowing about this specific hardware instruction, the LLM effectively reduced both the instruction count and the overall runtime overhead by potentially an order of magnitude or more. It transformed a multi-step iterative process into a single, highly optimized hardware primitive.
That's genuinely astounding. A single instruction replaced an entire loop. My mind immediately goes back to GCC03. Why can't decades of compiler engineering detect and apply such an obvious, powerful optimization if the hardware explicitly supports it? It seems like a no-brainer.
And this is precisely why this pop-and case study so powerfully highlights the LLM's unique potential and how it transcends traditional compiler limitations. Such a profound transformation is indeed beyond the reach of GCC03 and similar traditional compilers. They rely on that predetermined sequence of rule-based optimization passes we talked about. They operate by matching known patterns in the code, applying algebraic simplifications, transforming lower-level operations. But they typically do not conduct semantic-level rewrites of this kind, meaning they generally don't look at a block of C code, understand its high-level meaning or intent, like, aha, this loop computes population count, and then say, oh, I know a special instruction for that. I can replace that entire sequence with a single pop-and instruction. Instead, they apply their fixed rules to the more granular, lower-level operations within the loop itself.
So, the LLM, through its training, potentially including the reinforcement learning, somehow gains a higher-level understanding, almost an intuitive semantic comprehension of what the code snippet is trying to achieve. And then it can leapfrog the traditional rule-based optimization path to apply a more fundamental hardware-accelerated way to achieve that exact same result. That's a truly different way of optimizing code.
Exactly. This demonstrates the profound potential of language models to optimize assembly by exploring a far broader space of semantics-preserving program transformations. They're not bound by the fixed rule sets or the limiting phase ordering problems that constrain traditional compilers. Instead, through the iterative process of generation and feedback, especially with reinforcement learning, they can discover these more profound hardware-leveraging optimizations that require a deeper understanding of the code's purpose rather than just its structure.
This is truly impressive stuff, showing LLMs can genuinely do things compilers just can't, finding efficiencies that have eluded traditional methods for years. But like any powerful new technology, there are always important considerations and, future avenues to explore. So what does this all mean for the future of code optimization? And what are some of the current edges or limitations of this approach that need to be addressed before we all start using LLM-optimized assembly?
Yeah, this work provides a very strong proof of concept, a clear demonstration of capability.
Absolutely.
However, it's crucial to acknowledge the current limitations before we project too far into a future of fully autonomous code optimization. Understanding these boundaries is key to directing future research effectively.
Makes sense. So what are some of the key limitations of this current approach that the paper itself highlights? For instance, what about the critical aspect of correctness? We rely heavily on compilers to guarantee our code behaves exactly as expected.
That's probably the biggest one. A primary limitation, especially for safety-critical applications, is the current absence of formal correctness guarantees. While the approach meticulously validates generated programs using input-output test cases, such testing is inherently incomplete. As any software engineer knows, testing can show the presence of bugs, but rarely their absence. It can't possibly cover every single possible input or edge case for complex programs. This means that an LLM-generated assembly program might, under very specific unforeseen circumstances, produce wrong results or exhibit undefined behavior that just wasn't caught by the test suite used during training or evaluation.
Right. A hidden bug that only shows up under rare conditions.
Exactly. And this stands in contrast to some fully verified systems, like the super optimizer, Stoke, mentioned in the paper, which can mathematically prove semantic equivalence between the original and optimized code. That ensures the optimized code behaves identically to the original in all possible scenarios, a much higher bar. This limitation also reflects a broader, fundamental challenge in computer science and programming languages. Verifying the semantic equivalence between two arbitrary complex programs is, in the general case, mathematically undecidable, meaning there's no universal algorithm that can always give a definitive yes or no answer to the question, do these two programs always do the exact same thing? So while empirical testing, like they did, is practical and necessary, it's not exhaustive. It doesn't provide that ironclad guarantee.
That's a critical point for any system aiming for robust production-level code. Even a 99.9% pass rate isn't good enough if that 0.1% involves a catastrophic failure in a critical system.
Okay, what about the performance measurements themselves? You mentioned they used hyperfine and careful methodology, but real hardware can still be notoriously tricky and unpredictable, right?
Absolutely. Another significant limitation lies in the inherent randomness and variability of performance measurement on real hardware. Despite the diligent use of mitigation techniques like hyperfine with its warm-up runs and repeated executions, low-level hardware fluctuations can still creep in. Things like unpredictable cache misses, background OS processes kicking in, even tiny temperature variations affecting clock speeds, or slight shifts in instruction execution pipelines. All these can still introduce a degree of variability or noise into the speedup estimates. Such non-determinism is incredibly difficult to eliminate entirely in real-world settings. Now, while some prior research has adopted simulator-based evaluation to avoid this hardware noise,
Right, run it on a perfect predictable software model of the hardware.
Exactly.
But the problem there is that simulators themselves often fail to faithfully capture the actual complex hardware performance characteristics. They might miss subtle interactions or timings. So using simulators introduces its own set of inaccuracies. It's a constant balancing act between real-world relevance and measurement precision. There's no perfect solution right now.
so it's a dilemma. Real hardware is noisy and unpredictable, but simulators might not be accurate enough representations of true performance. Tricky. And finally, what about generalization? If a model is trained and achieves these impressive speedups on one specific machine, say, with a particular Intel CPU, will it perform just as well when deployed on a different machine with maybe an AMD CPU or just a different generation of Intel chip?
That's another significant practical concern, yes. The observed performance gains, impressive as they are, may not generalize perfectly across different machines or hardware configurations. An LLM, especially through reinforcement learning tuned on one machine, might implicitly learn and exploit very specific hardware characteristics of that training machine. Things like its exact cache sizes, the precise latencies of certain instructions on that particular CPU microarchitecture, or even subtle nuances of its memory subsystem. As a result, a model trained and painstakingly optimized on one specific machine may not retain its full effectiveness when deployed on a different machine with a distinct architecture, a different processor model, or even just slightly different memory configurations or BIOS settings. This is a long-standing challenge in high-performance computing and low-level performance tuning, and LLMs add a new layer to it. The model might overfit to the specific hardware it was trained on.
These are all incredibly important points to consider for any real-world deployment of this technology. Definitely food for thought. But putting these limitations aside for a moment, what's next for LLM-powered optimization? What are the exciting, promising frontiers for future research building directly on this groundbreaking work? Where do we go from here?
Well, despite the limitations, there are several truly promising avenues for future research building on this strong foundation. First, simply exploring alternative reinforcement learning algorithms beyond PPO. They mentioned GRPO as one possibility. Different algorithms could potentially yield further improvements or offer different trade-offs in training dynamics and convergence properties. It's a vast field, RL, with many innovative approaches still emerging. Second, and this is critically important for real-world impact, is expanding to larger and significantly more diverse data sets. While competitive programming problems are excellent for controlled experiments, focusing on performance-critical code beyond that domain would be huge. Think code from operating systems kernels, complex scientific computing libraries, graphics engines, databases, or even embedded systems code. Using these would make the setting far more realistic and broadly applicable to actual industry problems. More diverse code types should lead to more robust and generalizable optimization strategies.
Great. Moving beyond contest problems to the kind of code running critical infrastructure.
Exactly. Third, an intriguing area to investigate is combining reinforcement learning with supervised fine-tuning. It's an open question whether additional gains could be found by, for instance, first training the LLM on generating GCC03 outputs in a supervised manner before or perhaps during the reinforcement learning phase. This might give the model an even stronger foundational understanding of correct assembly generation before it even starts trying to optimize with RL, kind of a hybrid approach.
Interesting, like giving it a better baseline understanding first.
Potentially. Another fascinating direction is to incorporate an interactive refinement loop. Instead of a single one-shot code generation attempt, imagine the model iteratively updating its output. It could generate code, receive immediate feedback from compilation errors or performance measurements, maybe even from static analysis tools, and then refine its code in a loop until it meets a specific correctness or performance threshold. This would more closely mimic how a human expert iteratively tunes and debugs code.
Like a conversation between the LLM and the testing tools.
Something like that. Finally, and perhaps with the broadest potential impact, is extending this entire approach from the x86-64 architecture, which is dominant on desktops and servers, to other prevalent processor architectures. Moving from x86-64 to architectures such as MIs, common in older embedded systems and networking gear, ARM, which is dominant in mobile and rapidly growing in servers and laptops, or even specialized GPU programming environments like CUDA or ROCm. Successfully applying this there could significantly broaden its applicability and impact across the entire computing landscape, opening up new optimization possibilities for a vast array of devices and workloads.
That really raises an important question, doesn't it? Just how far can we push these models? The current work lays a strong, compelling foundation, that's clear. And the future clearly lies in addressing these fundamental challenges: correctness guarantees, robustness, generalization, and expanding their reach to new domains and paradigms. The potential for LLMs to become integral tools in optimizing complex software at its most fundamental level seems immense. It could really reshape how we think about code performance. So what does this all mean for you, the listener, at the end of the day? We've seen how large language models, armed with sophisticated reinforcement learning, can achieve truly remarkable speedups in assembly code, often beyond what traditional rule-bound compilers can do. This isn't just an incremental improvement in many cases. It seems like a potential paradigm shift, where AI can essentially think outside the box of predetermined compiler rules and discover genuinely novel efficiencies. We've unpacked the success of proximal policy optimization for this task, the surprising efficacy of sparse reward functions in driving aggressive speedups once correctness is established, and the absolutely crucial role of providing a high-quality baseline assembly from GCC03 as an effective starting point for the LLM's optimization efforts. It's really a testament to the power of combining human-engineered excellence, the compiler, with AI's ability to discover.
Absolutely, and this work really highlights, I think, a profound shift potentially happening in software engineering. We're moving perhaps from a world where we try to hard-code every optimization rule imaginable into compilers, as we've done for decades, to a future where we teach AI models to discover entirely new optimization strategies, maybe even ones humans haven't thought of, driven purely by performance feedback on target hardware. Now, while the fundamental challenge of formally verifying correctness in this ever-expanding optimization landscape remains a critical hurdle, then we can't forget that, the sheer potential for AI to continually uncover novel, hardware-specific performance gains is just immense. Imagine a future where your software doesn't just get compiled once with fixed settings. Imagine it learns to run faster on your specific hardware over time, dynamically adapting its low-level implementation to the unique microarchitectural characteristics of your CPU, your cache, your memory, rather than relying on generalized, one-size-fits-all compiler rules. That's a truly provocative thought for the future of software engineering, isn't it? Software that optimizes itself for its environment.
It certainly is. A future where software continually improves its own efficiency. Wow. Well, we hope this deep dive has given you a clear, engaging, and genuinely insightful look into the fascinating intersection of large language models and low-level code optimization. Keep that curiosity burning, keep exploring, and we'll be back with another deep dive soon.